Welcome to our latest video on the topic of alcohols, properties and preparation. This video is suitable for A-level students. By the end of this video lesson, you should be able to understand the intermolecular forces present in alcohols and how these are linked to physical properties such as boiling points. You should also be able to explain why alcohols with short hydrocarbon chains dissolve in water and why increasing the hydrocarbon chain in an alcohol reduces its solubility. And finally, you should be able to describe how alcohols can be prepared from halogenoalkanes, aldehydes, ketones and alkenes. Now, in our last video lesson, we introduced the homologous series alcohols and we learned how to name an alcohol. We also learnt how to classify an alcohol and we learnt the uses of alcohols. Now, alcohols have an OH functional group, and a functional group is the part of a molecule that determines its chemical reactions. Now, alcohols have the general formula CnH2n plus 1 OH, and the first two members of the alcohol family are drawn here. Methanol has a formula CH3OH, and ethanol has a formula C2H5OH. Both are alcohols because they contain the OH functional group. Now, we also learned in our last video lesson how to classify alcohols, and we learned that there are three types of alcohols: primary, secondary and tertiary. And primary alcohols have one alkyl group on the carbon next to the OH. Secondary alcohols have two alkyl groups on the carbon next to the OH. And tertiary alcohols have three alkyl groups on the carbon next to the OH. So let's look at an example. Here we have ethanol. Now, ethanol has a methyl group attached to the carbon next to the OH and two hydrogens. So as it has one alkyl group on the carbon next to the OH, it is classed as a primary alcohol. Now, classification is particularly important for alcohols because primary, secondary and tertiary alcohols do have some different reactions. So therefore it's important you can recognize what type of alcohol you have, whether it's primary, secondary or tertiary. Now, in the next section of this video, we're going to look at the physical properties of alcohols. We're going to look at alcohol's boiling points and we're going to look at the solubility of alcohols. Now, all alcohols are liquids at room temperature and pressure, and the boiling points and densities of alcohols increase with increasing relative molecular mass. So the boiling points of alcohols are much higher than alkanes with similar relative molecular mass, and this is due to the fact that alcohols have hydrogen bonds between their molecules. Now, hydrogen bonding is the strongest intermolecular force, and it occurs when you have a HO, a HN or a HF. And you can see I've drawn here the hydrogen bonding that exists between two ethanol molecules. And you can see that the delta H plus on one ethanol molecule attracts the delta minus oxygen on another. You should also notice that in my diagram to show hydrogen bonding between two ethanol molecules, I've included the lone pairs on the oxygen. Now, there are two lone pairs on each oxygen atom, and one of these lone pairs is contributing to a hydrogen bond. Now, hydrogen bonding, as we said, occurs with HO, HN and HF, and that's because fluorine, oxygen and nitrogen are the three most electronegative elements in the periodic table, and therefore their dipoles with hydrogen will be the three strongest. Now, it's also important to mention here that if you increase the alkyl chain in an alcohol, so in other words go from methanol to ethanol to propanol to butanol, etc., you increase the amount of van der Waals forces that exist between the molecules. Now, if you increase the alkyl chain, there are more electrons and there are more van der Waals forces. So therefore the boiling points of alcohols increase as you make the alcohol chain longer. Now the next property we're going to look at is solubility. And alcohols with short hydrocarbon chains dissolve in water because the OH group in the alcohol can hydrogen bond to water. Now, when we're talking about liquids dissolving, we really should use the word miscibility, because miscibility is a measure of how easily a liquid mixes or dissolves in another liquid. Now, the miscibility of alcohols in water decreases as the hydrocarbon chains get longer. And this is because the longer the hydrocarbon chain, the more it disrupts water's ability to form hydrogen bonds to alcohol's OH groups. So therefore, the most soluble alcohols are alcohols such as methanol and ethanol. And once you start getting to pentanol, hexanol, etc., the alcohols aren't very soluble in water. Now the following diagram shows ethanol hydrogen bonded to water. And you can see in this diagram that the delta minus oxygen on ethanol forms a hydrogen bond to the delta plus hydrogen on the water molecule. And you can also see in this diagram that a lone pair on the oxygen contributes to this hydrogen bond. So now let's test your understanding of the properties of alcohols with some practice questions. So here's our first practice question. Read through the question, pause the video, have a go at it, and then we'll go for the answers. So let's go for the answer to question 1. So the question is asking to explain why butan-1-ol is soluble in water, but 1-bromobutane is not. Now there's 3 marks for this. And if you said bromobutane cannot form hydrogen bonds, there's 1 mark for that. And if you said butan-1-ol can form hydrogen bonds due to its OH group, there's a mark for that. And if you said that hydrogen bonds can form between butan-1-ol and water molecules, and this allows butan-1-ol to dissolve, you get the 3rd mark. Now, some people will prefer to draw a diagram here to expand their answer, and I'm going to show you a suitable diagram that you could draw. Now, if I had to explain why any alcohol dissolves in water, I would draw a diagram. So I'm going to draw butan-1-ol here, and in butan-1-ol I have the OH on carbon 1. Now I don't have to put the bond between the O and the H, but I've chosen to do that here in this diagram. So I'm putting all the hydrogens in around the carbons, and then I'm going to put the dipole that exists on the O and the H. So the oxygen is delta minus and the hydrogen is delta plus. Now the reason that butan-1-ol dissolves in water is it can form hydrogen bonds to water. So I'm going to draw in a water molecule here, and I'm going to put in the dipoles, delta minus on the oxygen, delta plus on the hydrogen. And this water molecule hydrogen bonds to the alcohol's OH group. So I'm going to put in the lone pairs on the oxygen, and there's 2 lone pairs on the oxygen in butan-1-ol, and there's 2 lone pairs on the oxygen in water. And one of these lone pairs contributes to the hydrogen bond. So I'm now going to put in the hydrogen bond, and I'm going to represent this with a dashed line. So if I drew a butan-1-ol molecule and just drew water forming hydrogen bonds to the OH group on the alcohol, and then put a few bullet points to explain my diagram, that would be a pretty good way of answering this question. However, the reality is that water gets in between the alcohol molecules. So you will find that what really happens is that the water molecule that is forming a hydrogen bond to the OH group here can form another hydrogen bond to another alcohol molecule. So I'm going to draw more hydrogen bonds here between my water molecule and my second alcohol molecule. And I'm going to represent this hydrogen bond with a dashed line, and once again I'm going to put my lone pairs around the oxygens, and you can see that a hydrogen bond could form here between the delta plus hydrogen on water and the delta minus oxygen on my second alcohol molecule, and I've still got a lone pair free on the oxygen to form a hydrogen bond to the delta plus hydrogen on my second butan-1-ol molecule. So my diagram shows that water gets in between the alcohol molecules. So now let's have a go at a second practice question. Once again, pause the video, read through the question, have a go at it, and then we'll go for the answers. Now question 2 is asking why the boiling temperature of methanol is higher than the boiling temperature of chloromethane, and there's 3 marks for this question. Now to answer this you need to talk about the intermolecular forces that exist in methanol and chloromethane. Now methanol has hydrogen bonding between its molecules, so you said that, there's 1 mark. Chloromethane has van der Waals forces between its molecules, or you could say permanent dipole forces between the molecules. There's 1 mark for that. Hydrogen bonding is a stronger intermolecular force than van der Waals. If you said that, you get the 3rd mark. And because hydrogen bonding is a stronger intermolecular force, more energy is needed to pull the molecules apart. So now have a go at question 3. Once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So question 3a is asking you to explain why the boiling points of alcohols increase as the number of carbons in the chain increases. Now this is because the longer the hydrocarbon chain, the more electrons there are, 1 mark for that, and the more van der Waals forces there are, 1 mark for that. And that's why more energy is needed to pull the molecules apart. Now for question 3b, you're asked to explain why the solubility of alcohols decreases with increases in hydrocarbon chain length. Now this is because the hydrocarbon chain is non-polar or hydrophobic. There are no dipoles in the hydrocarbon chain. 1 mark for that. And the longer the hydrocarbon chain, the more it disrupts water's ability to form hydrogen bonds to the alcohol's OH group. And if you said that, there's 1 mark. Now in the next section of this video, we're going to look at the different ways that alcohols can be prepared. And our first way of making an alcohol is from a halogenoalkane. Now if we heat a halogenoalkane with aqueous alkali such as sodium hydroxide or potassium hydroxide, and we heat it under reflux, we will form our alcohol and halide. So if we have chloromethane and sodium hydroxide, we make methanol and sodium chloride. And this reaction is a nucleophilic substitution reaction. And in the reaction, the OH swaps with the halogen atom. So here we have CH3Cl plus NaOH makes CH3OH and NaCl, and all that's happened is the OH has swapped with the Cl. So now let's test your understanding of this with some practice questions. Read through the questions, pause the video, have a go at them, and then we'll go for the answers. So for this first practice question, we're asking you to complete the following word equations. So for question 1a, it was bromoethane and potassium hydroxide. So this would produce ethanol and potassium bromide. And for question B, it was chloroethane and sodium hydroxide. So that would produce ethanol and sodium chloride. And for question C, iodomethane and ammonium hydroxide would produce methanol and ammonium iodide. And question 1D is chloroethane and potassium hydroxide that would produce ethanol and potassium chloride. And there's 1 mark for each correct answer here, completing these word equations. So now have a go at our second practice question. So we'd like you to complete the following chemical equations. So read through the question, pause the video, have a go at it, and then we'll go for the answers. So now let's go for the answers to question 2. So 2a is CH3Br plus KOH, and that would produce CH3OH and KBr. And for question 2b, we have CH3CH2CH2Cl plus NaOH, and that would be CH3CH2CH2OH and NaCl. That's what would be produced. And for C, we have CH3CH2I plus NH4OH, and that would produce CH3CH2OH plus NH4I. And then for the last one, CH3Cl plus KOH would produce CH3OH plus KCl. And there's 1 mark for each correct equation here. Now our second way of making an alcohol is from alkenes. If you react an alkene with steam at 300 degrees C and a pressure of 60 to 70 atmospheres using a catalyst of phosphoric acid supported on silica, you will produce an alcohol in an exothermic reaction. Now this reaction is important as it's the way that alcohol is produced industrially. It's a continuous process where alcohol can be produced 24 hours a day. Now the reaction is reversible and the conditions are there to allow us to have a reasonable yield at a reasonable rate. Now the reason that we have a high pressure in this reaction is because when you increase the pressure, the equilibrium shifts to the side of lowest number of moles of gas. Now that is the right hand side. So therefore increasing the pressure causes the equilibrium to shift to the right hand side, and therefore the yield increases. So you get a better yield at a high pressure. Now this reaction is exothermic. So a low temperature would give you the best yield because a low temperature would cause the equilibrium to shift to the right hand side, the exothermic side. However, a low temperature is not used here because the reaction would be too slow. So they use a temperature of 300 degrees C and they don't go any lower than that because the reaction would be too slow. Now they don't go higher than 300 degrees C because although the reaction would be faster, the yield would be worse because if you increase the temperature, the equilibrium would shift to the left hand side, the endothermic side. Now our third way of making an alcohol is from an aldehyde or ketone. And aldehydes and ketones contain a carbonyl group, a C double bond O group, and in aldehydes the carbon atom of this group is joined to at least 1 hydrogen atom. So the general formula of an aldehyde is R C double bond O H. Now the full structural formula of 2 aldehydes are shown here. Ethanal has a CH3 bonded to a C double bond O H, and propanal has a CH3CH2 C double bond O H. Now in a ketone, the carbonyl group, the C double bond O, is joined to 2 other carbon atoms. So the simplest ketone must contain at least 3 carbon atoms. So here's the general formula of a ketone is R, C, double bond O, R. And R represents an alkyl group. So 2 examples of ketones are drawn here. The first is propanone, and this is CH3, C double bond O, CH3. So you can see 2 alkyl groups are attached to this C double bond O. And my second example here is butanone, which is a CH3 bonded to a C double bond O, C2H5. Now we're not going to worry too much about naming aldehydes and ketones in this video because in later videos we'll be studying aldehydes and ketones in much more detail. Now, alcohols can be formed by the reduction of an aldehyde or ketone, and reduction is a term used to describe a gain of hydrogen, a gain of electrons, and a loss of oxygen. Now, when an aldehyde gains hydrogen, it turns to a primary alcohol. And if we look at our general formula of an aldehyde, you can see that we have one R group, one alkyl group. And when we reduce this aldehyde, it turns to an alcohol with one R group, with one alkyl group. And that's why it's classed as a primary alcohol. So when you reduce an aldehyde, you get a primary alcohol. And if we look at this slide, you can see ethanol can be reduced to ethanol. Now, if you look at the structure of ethanol compared to ethanol, you can see that ethanol has two extra hydrogen atoms. It contains a hydrogen next to the oxygen and another hydrogen on the same carbon next to the oxygen. So there's been a gain of hydrogen here as ethanol has changed to ethanol. Now, when reducing an aldehyde or a ketone, we cannot use hydrogen gas. Now, this is because aldehydes and ketones react with nucleophiles, and we need a nucleophilic form of hydrogen. So the reducing agents we use are a nucleophilic form of hydrogen, and there are two reducing agents you need to learn for the exam. The first is sodium borohydride, NaBH4, and this reducing agent works in water in aqueous solutions. Now, the second reducing agent you need to learn that we could use here is lithium aluminium hydride, LiAlH4. Now, this is a much more powerful reducing agent, and lithium aluminium hydride is used in dry ether. You can't use water with lithium aluminium hydride because it's so powerful it will reduce the H+ ions in water to hydrogen gas. So sodium borohydride is carried out in water as a reducing agent, and lithium aluminium hydride works with dry ether, a non-aqueous solvent. Now, if we reduce a ketone with these same reducing agents, sodium borohydride in water or the more powerful lithium aluminium hydride in dry ether, we will end up with a secondary alcohol. And an example here is propanone, which is reduced to propan-2-ol. Now, a ketone contains two R groups, two alkyl groups, and therefore the product of reduction contains two alkyl groups. And that's why a secondary alcohol is formed with a ketone when you reduce it. Now, if you look closely at this example here, propanone being reduced to propan-2-ol, you can see that propan-2-ol contains two additional hydrogens. There is now a hydrogen next to the oxygen to form an OH, and on the same carbon that the OH is joined, there is an additional hydrogen. And that's what's happened when propanone has changed to propan-2-ol. The molecule has been reduced, it's gained hydrogen. So we've now discussed two further ways of making an alcohol. In other words, the addition of steam to an alkene and the reduction of aldehydes and ketones. So now let's test your understanding of these methods with some practice questions. So read through the questions, pause the video, have a go at them, and then we'll go for the answers. So our first practice question is asking why ethanol is classed as a primary alcohol. Now, it's classed as a primary alcohol because if you look at the carbon next to the OH group, there's one alkyl group attached to this carbon. So ethanol is a primary alcohol because there's one alkyl group attached to the carbon next to the OH group. Now question 2 is asking you to draw the aldehydes that can be used to prepare methanol, propanol and butan-1-ol. So first of all I'm going to draw methanol, and remember, to make the primary alcohol methanol, an aldehyde must have been reduced. In other words, an aldehyde had hydrogen added to it. So I'm just going to take away the hydrogen from this primary alcohol so I can see the aldehyde that was needed to make methanol. And if I remove the hydrogen from my primary alcohol, I'm left with this aldehyde, which is HC double bond OH, and this aldehyde is called methanal. So question B is asking which aldehyde is used to make propan-1-ol. So I'm going to draw propan-1-ol, and in propan-1-ol I'm going to put an OH group on the end carbon, carbon 1, and I'm going to put in all the hydrogens, and then all I'm going to do is remove 2 hydrogens from propan-1-ol. I'm going to take away a hydrogen that was attached to the oxygen, and I'm going to take another hydrogen away from the carbon that the OH is joined to. Now that will leave me with the aldehyde that is used to make propan-1-ol, and this aldehyde is going to be called propanal. So I'm just going to put in the last few hydrogens, and there we have the aldehyde propanal that is reduced to form propan-1-ol. So for question C, I'm asked to draw the aldehyde that forms butan-1-ol when it is reduced. So first of all, I'm going to draw butan-1-ol, and in butan-1-ol there's an OH group on carbon 1. So I'm now going to put in all the hydrogens for butan-1-ol, and then all I'm going to do to find out the aldehyde that is reduced to form butan-1-ol is remove hydrogen from butan-1-ol. So I'm going to take away the hydrogen next to the oxygen, and I'm also going to take away another hydrogen that's attached to the carbon next to the OH. And that will leave me with the aldehyde that is reduced to form butan-1-ol, and this aldehyde is called butanal. Now it's worth reinforcing that a primary alcohol has one alkyl group attached to the carbon next to the OH, and in an aldehyde we also have one alkyl group present, and that's why reduction of an aldehyde gives a primary alcohol. So therefore the aldehyde that is reduced to form butan-1-ol is butanal. So here are 2 more practice questions we'd like to have a go at. So once again, read through the questions, pause the video, have a go at them, and then we'll go through the answers. So question 3 is asking why propan-2-ol is classified as a secondary alcohol. Now it's classed as a secondary alcohol because there are 2 alkyl groups attached to the carbon next to the OH. And you can see in this diagram that the 2 alkyl groups are both CH3 groups, methyl groups. So for question 4, you're asked to draw the ketones that are reduced to form butan-2-ol, pentan-2-ol and pentan-3-ol. So let's start with butan-2-ol. So butan-2-ol has 4 carbons in the chain, and there's an OH group on carbon 2. So I'm going to put my OH group on carbon 2, and then what I'm going to do, just as I did with the previous questions, I'm going to remove hydrogen from this molecule. I'm going to take a hydrogen away from the OH group, and I'm going to remove another hydrogen from the carbon next to the OH, and that will leave me with my ketone. So I'm going to take the hydrogen here from the OH, I'm going to take the hydrogen away from the carbon next to the OH, and I'm left with butan-2-one, which is a ketone. So I've got to remember to put in my double bond and put the hydrogens around the carbons, and therefore we have the ketone that is reduced to form butan-2-ol. Now this ketone is called butan-2-one. However, it can be simply called butanone because when you're naming a ketone, the number indicates the position of the C double bond O, and it can only be on carbon 2 here because there's no other place it can be and still be a ketone. So therefore you could call it butan-2-one or butanone. So for question 4b, I'm asked to draw the ketone that is reduced to form pentan-2-ol. So the first thing I'm going to do is draw pentan-2-ol. So I have to draw an alcohol with 5 carbons in the longest chain and then put an OH group on carbon 2. So I'm just putting the hydrogens around the carbons now, and when I get to carbon 2 I'm going to put an OH group, and then what I'm going to do once I've drawn pentan-2-ol is I'm going to remove hydrogen from this molecule. So I'm going to take a hydrogen away from the OH group, and then I'm going to take a hydrogen away from the carbon next to the OH group. So if I take away these hydrogens now, so one from the OH group and one from the carbon next to the OH group, I'm going to end up with my ketone. And my ketone has a C double bond O on carbon 2. Now this time it is important that I name it correctly and call it pentan-2-one because there is a ketone where the C double bond O is on carbon 3, and that's called pentan-3-one. So this time I can't just call it pentanone, I have to call the ketone pentan-2-one. So when pentan-2-one is reduced, I will get the secondary alcohol pentan-2-ol. So for question 4c, I'm asked to draw the ketone that is reduced to form pentan-3-ol. So once again, I'm going to start with pentan-3-ol, and pentan-3-ol has 5 carbons, and this time has an OH group on carbon 3. So I'm going to put in my hydrogens, and I have to remember that the OH group is on carbon 3, so I'm going to put in my OH group now. And then once I've drawn pentan-3-ol, I'm going to remove hydrogen from this molecule, and I'm going to take away a hydrogen from the OH group, and then I'm going to take away a hydrogen from the carbon next to the OH group. So here's my pentan-3-ol. Let's take away now the hydrogen from the OH group and the hydrogen from the carbon next to the OH group, and that's going to leave me with a ketone, and this ketone is called pentan-3-one. Now the ketone is called pentan-3-one because there's 5 carbons in the ketone and the C double bond O is on carbon 3. And it's important that we call it pentan-3-one and not pentanone because we've seen previously that there's a ketone called pentan-2-one where the C double bond O is on carbon 2. So this is called pentan-3-one and it reduces to form pentan-3-ol. So here's our last practice question, question 5. So once again, read through the question, pause the video, have a go at it, and then we'll go for the answers. So question 5 says that ethanol can be formed by reacting ethene with steam at 300 degrees C and a pressure of 60 to 70 atmosphere with a catalyst of phosphoric acid supported on silica, and the equation is shown. Now it's asking why high pressure is needed in this reaction. So this is a 2-mark question. Now the reaction is reversible. So if you increase the pressure, the equilibrium shifts to the side of lowest number of moles of gas. Now there's 2 moles of gas on the left and 1 mole of gas on the right. So increasing the pressure causes the equilibrium to shift to the right hand side, the side of lowest number of moles of gas, and this gives a higher yield of ethanol. So there's 1 mark if you say that the equilibrium shifts to the right, the side of lowest number of moles of gas, and there's 1 mark if you said this would give a higher yield of ethanol. Now for question 5b, you're asked why a lower temperature is not used in this reaction, even though it would lead to a higher yield of ethanol. Now, if you had a low temperature, the equilibrium shifts to the side that gives out heat, which is the right-hand side, because the forward reaction is exothermic. However, the reason a low temperature is not used here is because a low temperature would give you a slower rate of reaction. It would give you a lower rate or a slower rate of reaction. So that's why they don't use a lower temperature. 300 degrees C is a compromise temperature. It gives you a reasonable yield at a reasonable rate. So that concludes our video lesson. So after watching this video, you should now understand the intermolecular forces present in alcohols and how these are linked to physical properties such as boiling points. You should be able to explain why alcohols with short hydrocarbon chains dissolve in water and why increasing the hydrocarbon chain in alcohol reduces its solubility. And finally, you should be able to describe how alcohols can be prepared from halogenoalkanes, aldehydes, ketones and alkenes. So that concludes our video. Please check out our YouTube channel, Dr. O Chemistry, and our Twitter site, which contains lots of chemistry information and links, @RadaChemistry.